Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Starting with the name of Allah, the most merciful and beneficent. Today, in this lecture, we will start chapter number 4, time response. And in this chapter, we will discuss the topics which are mentioned over here. Before starting this chapter, let us take a quick review of what we have done up till now. So, in chapter number 1, we have discussed the analysis and design objectives, the design process, and also some standard test inputs. And in chapter number 2, modeling in frequency domain, we have learned that how the schematics that are representing the physical systems can be represented mathematically in terms of differential equation, and then we convert these differential equations into S or frequency domain, and then we solve these differential equations to formulate the transfer function. And the transfer function is nothing but the representation of the system in frequency domain. And in chapter number 3, that is modeling in time domain, we again develop mathematical models of various systems in time domain and then solve them to formulate the state and the output equations. We also discuss the pros and cons of these two modeling techniques. Now, according to the design process, which we have covered in chapter number 1, we first create a schematic of a physical system, and then develop a mathematical model of that schematic, and then further we reduce the mathematical model into a mathematical description in terms of input and output. And then the last step of this design process is to analyze and design the system. So the first 3 steps of the design process were covered in chapter number 1, 2 and 3. And now in chapter number 4, we will learn how to analyze and design a system. So for this, let us take an example of a fan. When we switch on the fan, it starts accelerating, and after some time it attains a fixed speed. And if we draw its output response, then it will be look like So this is the output response of the fan, and this response we can also say it as the time response. And we know that this output response or time response contain two parts, that are the transient, this is the transient part, and this steady state part. So I can write it as the output response is the sum of the transient response and the steady state response, or the natural response or the forced response. And if we want to analyze this system, we have to analyze these two responses, namely the transient response and the steady state response. There are many techniques to analyze the output responses, such as solving differential equation or taking the inverse Laplace transform. But the problem is that these techniques are very much time consuming. So we have to find an alternate way or technique that enable us to develop the result in a minimum of time. So we will use two parameters, that are poles and zeros. These parameters enable us to analyze the output response and also enable us to derive the desired results directly by inspection. So first we discuss their definition, definition of poles and zeros, and then we will discuss how they will help us to analyze a system. Poles. The poles of the transfer function are the values of the Laplace transform variable s. That causes the transfer function to become infinite. So if we have a transfer function, this g of s, 8. So the values of the roots that are present in the denominator are basically the poles, because if I put here s plus 8 is equal to 0 or s is equal to minus 8, it will cause this transfer function to become infinite. Zeros of transfer function. The zeros of the transfer function are the values of the Laplace transform variable s that causes the transfer function to become 0. So the roots that are present in the numerator of this transfer function, which is s plus 3, will make this transfer function to 0. Means if s plus 3 is equal to 0, or I can write it as s is equal to minus 3. If I put s is equal to minus 3 in this transfer function, then it will make it 0. So to understand the concept of poles and zeros, let us take an example of a first order system. Here the input R of s and the output will be C of s, and this is the transfer function G of s. According to the definition of poles and zeros, the numerator term s plus 2 is our 0, because it causes the transfer function to become 0, and the term which is present in the denominator, which is s plus 5, is our pole, because this s is equal to minus 5 term will cause this transfer function to become infinite. We can also plot these poles and zero in the complex S plane. This is our complex j omega axis, and this is our real axis. So if we want to plot this 0 here at -2, we will use a 0 sign to represent this 0, and to show this pole s equal to -5, we will use this cross sign. So the pole will be represented by the cross sign, and the 0 will be represented with 0 sign. Now to show the properties of poles and zeros, let us find the unit step response of the system. So if we apply the unit step response, then R of s become 1 upon s. So I can write it as g of s will be equal to c of s upon R of s, or c of s upon 1 upon s, which is equal to this term s plus 2 s plus 5. So if we cross multiply this 1 upon s term, then it will become s plus 5. To solve it, we have to use the partial fraction technique. So I have to break these roots into two terms, a upon s and b upon s plus 5. Now to find out the values of these constants a and b, I am multiplying this equation 1 with this denominator term. S plus 5. So here s plus 2 will be equal to a of s plus 5 and b of s. So I am saying this equation as equation number 2. Now I first put s is equal to 0 in this term to find the value of a. So this s will be 0, and here also s will be 0, and this whole term becomes 0. So the value of a will be 2 divided by 5, and to get the value of b, we put s plus 5 equal to 0 in equation 2. So now here s become 5, s is s plus 5, or s is equal to minus 5. Minus 5. So we have to put over here minus 5 plus 2, and this term will become 0, and here also b will be multiplied by minus 5. Here minus 3, and this sign will be cancelled, and the value of b becomes 3 upon 5. By putting the values of a and b in equation 1, we will get c of s equal to 2 upon 5 upon s plus 3 upon 5 divided by s plus 5. Now if we will take the inverse Laplace transform, then we will get the output response as 2 upon 5 plus 3 upon 5. This term become, this s plus 5 term becomes e की power minus 5t u of t. Now we know that our input pole is 1 over s, and system 0 is s plus 2, and the system pole upon s plus 5. So if we draw these values or plot these values on s plane, then this 1 upon s will be plotted over here, because here the value of s is equal to 0, and this 0 will be plotted as here minus 2, and this pole will be plotted as here. Our output transform is equal to C of s as we calculate it earlier, and the output time response is this. So this 1 upon s term in this output transform is come from this input pole, means this input pole produces this S term here, and the system pole -5 over here is responsible for this S plus 5 term, and this 0, system 0, is responsible for these constant terms, and in this output response, this constant term 2/5 is come from the input pole, and this term, this exponential term, comes from the system pole. So we know that the exponential term having negative power, and if its power increases, means this 5 is multiplying, this 5 is multiplying with the time, and if time increases, the power of this exponential term increases. So after some time, this whole term become 0. So when this whole term becomes 0, only this 2/5 term, which is basically comes out from our input, will exist, and this value become 0. So if I plot its output response, then it will be look like this. After some time, this transient becomes 0, this transient part becomes 0, and only this part, this constant part remain in the system. So I can say that this is our forced response, or steady state response, and this is our transient response or natural response. So from the above discussion, we concluded that a pole of input function generates the form of force response. And a pole of the transfer function generates the form of natural response. and a pole on the real axis generates an exponential response. The zeros and poles generates the amplitudes for both forced and natural response. If we look over here, then this pole at origin, which is our input pole, produces this force response part, and this system pole, which is over the real axis, produces this transient part, and this transient part consists of this exponential term, and the system 0 is responsible for this constant terms. Let us now look at an example to observe the significance of using poles to write the form of the output response. Given the system, the transfer function of the system will be look like S plus 5. This is the transfer function. Here the input will be applied, and from here we get the output. So we have to write the output in time domain in general terms. Also we have to specify the forced and natural responses, natural parts of the solution. In this question we have to write the output in general terms. So our transfer function is and s plus 5. This is our transfer function. Since we have to find the output, so for that we have to apply an input. So I am assuming that our input is unit step, so I can write here 1 over s in place of r of s, our input. So this is the transfer function, s plus 2, s plus 4 and s plus 5. Now this value will be cross multiplied over here. It will be look like this. So we have to find our output response in time domain. So for that we have to take the partial fraction here. Here as b upon s plus 2, c upon s plus 4, and our last term will be b upon s plus 5. Normally we calculate the values of these constant terms, but in this question we have to represent our output in general terms, so we are not calculating the values of these constant terms. We will apply here in this step inverse Laplace transform. In this step. So from here we can write our output response as A plus this term becomes B e की power minus 2t, because this s plus 2 term will become this exponential term, and similarly C e की power minus 4t and D e की power minus 5t u of t. So this is our output response in general form. Now we have to specify, as we are asked in the question, to specify the forced and the natural parts of the solution. So from here we can tell that this constant term having no exponential term, which comes from this input part, this input pole. So this is our forced response. And all the other three terms which we get from our system poles, these three terms are come out from the system poles. So these three terms will be responsible for the transient response. So we can conclude that the input pole at origin produces the force response, this force response, and the system poles on the real axis produce the transient response. So from this example, it is clear that the poles of the transfer function is a very important parameter that directly represent the form of output response by inspection without having any lengthy mathematical solution. In the next lecture, we will start our discussion on first order system. Thank you.